Okay, in this section, we will explore how the COMxL can be used to solve 2D linear programming problems, where we will employ the use of the 2D constraint grapher. So, in this worksheet, we have our optimization problem on the far left. So we have our problem 1, that is to minimize the function 6x1 minus x2, subject to our constraint 3x1 minus x2 equal to 4, 2x1 plus x2 equal to 3, and minus x1 minus x2 equal to minus 3. And x1 and x2 must be non-negative integers. So here is a three-dimensional linear programming problem, and we can employ the use of the 2D constraint grapher. So to feed in the results, to feed in the variables into the 2D constraint grapher, we extract the coefficient of our constraints. So for the first constraint, we have 3x1 minus x2. So in one cell, we have the 3, that's the coefficient of the x1, minus 1 for the coefficient of the x2, and our symbol. Now, the constraint grapher can accept constraint of the form greater or equal to, less or equal to, less than, equal to, and greater than. So there are 4 signs that it can work with: greater or equal to, less or equal to, less than itself, greater than itself, and also equal to. Now, this constraint is of the term greater or equal to. So we extract the coefficient of the first term, that is the 3 for x1, minus 1 for x2, our symbol, and the constant on the far right. Then we do same for the other constraints. The constraints in the worksheet must be followed by each other. So for one constraint, it must be on a continuous column in the same way, and the next should be on the next row. So over here we have our input. So to plot our constraints, we start our 2D constraint by writing on the 2D constraints button. So we have only one input, one major input, that is cell with coefficient. So we click on this and we select our constraints cells, and we click on plot, So we have this term over here. Now since the x1 and x2 must be non-negative integers, I can readjust my x2 axis to start from 0. And also, for the plot over here, my x2 the maximum is going to be around 3. So I can readjust the maximum of the x2 axis to say 5. And my major term, so on the far left axis we have 0, 2, 4. I can make it 1. And my minus is 0.5. On x1 axis interval, I make from 0 to also 4. And I will plot the constraints. So we have this. Now in these constraints, the first is for the first constraints, that is C1, we have C2 for second and C3 for third constraint. Now to test the region of visibility, we have this bottom side of the graph over here. It says the visibility tested. So we come into our plots. We have several areas of the plot. We have this area, region 1, region 2, region 3, region 4, region 5, and a very small region on the x1 axis. So to test for the region of visibility, you come to the regions and you pick point in the region to test. So if I come to this region, I pick say 0.5 for x1, 0.5 for x2. So 0.5 x1, 0.5 x2, and I test it. It says invisible. So this region is an invisible region. So I come here, I pick 1 for x1 and 1.5 for x2. So 1 for x1, 1.5 for x2. My test invisible. If I come to the top here, I pick 1 for x1 and 4 for x2. So 4 for x2. It says invisible. If I come to this constraint, this region, I pick 2 for x1 and 0.5 for x2. So 2 and 0.5. It says visible. So this region on our constraint graph is the visible region of the objective of the linear programming problem. If I come to this last region, just to test, I pick 3 and 1. So 3 for x1, 1 for x2. My term I could say invisible. So this is our region of visibility. So I will readjust my x1 axis to start from 1, and then that's 3 to get our optimal point. Now it says x1 and x2 must be non-negative integers. So looking at the x1 axis, we have only two integers here, 2 and 3. And in the x2 axis, we have 0 and 1 in that same region. So the 2 and 1 forms one integer point in the region of visibility, and the 3 and 0 form one integer point in the region of visibility. So I take my points 2, 1 and point 3, 0, and I test it in the objective function. That point which will give me the minimum value of the objective function becomes my optimal point. So I can save this to my worksheet. So it's on the worksheet now. Now for the next problem, it says maximize the function 3x1 plus 4x2 subject to this constraint. So I do say I extract my equation of the constraints. So 7, 11 is less or equal to and 8 is. So 3 minus 1 less or equal to 12. And I notice. So I select my, yeah, I want, okay, let me just plot it first. So this is the graph of constraints. So from 0 to let's say 10, I want it to be from 1 increment 8.59. I'll leave my x-axis, x1 axis to 0 to 8, and I'll go plot it. So we have four regions on the constraint graph: region 1, region 2, region 3, region 4. So I want my visible region. So I pick points in the regions to test. If I come to this region, I'll use point 1, 1. So 1, 1. It says feasible. So this is our feasible region. If I come here, I will say 3, 9. That would be this point in this region. So 3 for x1, 9 for x2. It says infeasible. So this is an infeasible region. If I come here, I'll pick 6 and 2 or 6 and 1. So it's 6 and 2. It's also infeasible. And if I come to the top region, this, I'll pick 7 and 6. So 7 and 6 is also infeasible. So we have this to be our feasible region. But the goal here is to maximize the function by taking x1 and x2 values as integers. So I look in this region. So let me readjust my axis. I will set my x2 axis to 8. Now I set my x1 axis to 6. So I have it as this. So looking at our constraint graph, we have several regions in there that are integers. So if I come here, we have 0, 8. If I come to 0, 7, here is 1, 7, here is 2, 6, 3, 6, 4, 5, 5, 4. So there are several integer points in the region of visibility. So you pick any of those points, that will give the maximum of the objective function. But then since we are talking about maximum of the function, then we first have to test the points at the extremes of the constraints. So 0, 8, 1, 7, 2, 6, 3, 6, 3, 5, 4, 5, 5, 4, 5, 3. So we test those points first to see if any will give us the maximum region. The reason being that the points at the ends of the constraints are much higher points than the points below the constraint or in the inside of the constraints. So that for the 2D constraint grapher with the COMxL.